Hello and welcome. Today, we dive into the shadowy world of wartime intelligence and the incredible technological chess match over Europe's skies during 1943. A contest where a single aircraft, captured behind enemy lines, would reveal unsettling truths about modern industrial warfare. Imagine a fighter, battered and fuel-starved, making a desperate landing in French farmland, only to be surrounded by the very enemies it had battled moments before. German engineers now examining an American P-47 Thunderbolt, nicknamed Beetle, with a relentless curiosity that would forever change their understanding of American manufacturing might. How did this massive aircraft, with its 8 machine guns and armor that defied German rounds, challenge German assumptions about what a fighter could be? Could a captured plane, dissected piece by piece, turn the tide of a war driven as much by factories as by fighters? What if the Germans, after hours of meticulous testing, uncovered that the Thunderbolt's armor absorbed hits from their cannons, that it could limp home after taking severe damage, and that its turbo-supercharged engine maintained full power at altitudes where German fighters faltered? Did they realize that this aircraft embodied not just American engineering resilience but a new era where industrial capacity, not just pilot skill, determined victory? And what was the ultimate lesson learned? That material superiority, when harnessed in overwhelming quantities, could render even the most agile or well-designed German fighters almost irrelevant. In this story, the fate of a single aircraft symbolizes a broader truth. By late 1943, the outcome of the air war was no longer solely about tactics or pilot prowess but about the staggering scale of American industrial production. Over 125,000 engines, tens of thousands of fighters, and a logistical network capable of sustaining continuous, overwhelming assault. How did the Germans, with their limited resources and crumbling factories, hope to compete against such a relentless industrial juggernaut? Could the knowledge gleaned from that captured Thunderbolt give them a fighting chance, or was it already too late? This is a story of secrets uncovered, of factories and factories of steel and aluminum that made the American war machine unstoppable, and of how, in the end, the greatest weapon was not just the aircraft itself but the vast, intricate system that built it. The most dangerous question remains: are the lessons of this aircraft and its captured insights a warning that in modern war, victory belongs not only to the brave but to the vast capacity to produce, innovate, and outlast? The journey begins now. On the 7th of November in the year 1943, at Karpik airfield in the French region of KH, an intense and treacherous atmosphere hung over the battlefield. The formidable headwinds battering the English Channel had severely drained the fuel reserves of the aircraft involved. Second Lieutenant William E. Roach, a seasoned pilot assigned to the 358 Fighter Squadron within the 355 Fighter Group, was keenly aware of the perilous situation looming before him. As he monitored his gauges, he saw the needle inching dangerously close to the empty mark, his Pratt & Whitney R2800 engine sputtering ominously as fuel scarcity worsened. Roach stood at a crossroads, faced with an impossible dilemma: to press on toward the safety of England, which was tantalizingly within reach yet, given his dwindling fuel reserves, virtually unattainable at that moment. Beneath him unfurled a mosaic of French farmland, a mixture of terrains, some familiar and allied, many under the control of German forces. One airfield, in particular, caught his eye. Its layout and structures bore a striking resemblance to the Allied bases he knew well. Despite the chaos and the peril, Roach made a calculated decision to commit to his landing approach, trusting his skills and the aircraft's resilience. The massive Republic P-47D Thunderbolt, bearing the serial number 42-22490 and affectionately nicknamed Beetle, glided gracefully onto the grass runway, a testament to its robust design and strength. As he taxied toward a designated parking spot, Roach followed a ground vehicle that guided him to a holding area. Only after shutting down his engine did he notice the Balkan Crow insignia on the nearby aircraft, a stark reminder of the enemy he had engaged just moments earlier. In a cruel twist of fate, the very Germans he had been battling now encircled his aircraft with rifles aimed at his cockpit, a stark illustration of how quickly the tides of war can turn. For Lieutenant Roach, the chapter of active combat had concluded. His war as a combat pilot was effectively over. Yet, the story was far from finished. The aircraft he left behind, Beetle, was about to serve as a formidable and unexpected teacher for his captors. One whose lessons would challenge and reshape their understanding of American industrial and technological prowess in ways no one could have foreseen. When German engineers and technicians examined the captured P-47, they uncovered insights that would profoundly influence their perceptions of American manufacturing and innovation. The P-47 Thunderbolt was more than just a formidable fighter aircraft. It embodied the very ethos of American engineering excellence, industrial capacity, and material abundance. For the next year and a half, German specialists would meticulously disassemble, test, and attempt to fly the captured Thunderbolts. Through their diligent efforts, they would be forced to confront a disconcerting realization. Germany was not merely lagging behind in a technological race but was fighting in an entirely different league of industrial warfare. The story of the captured P-47s, especially those falling into German hands, reveals a stark truth: material superiority, when effectively harnessed in military aviation, could render tactical skills and pilot proficiency increasingly irrelevant in determining the course of a conflict. The formidable power of the American Thunderbolt demonstrated how overwhelming technological and industrial dominance could tilt the outcome of aerial combat. Though German engineers would learn valuable lessons from their examination of the Thunderbolt, the real challenge lay in applying that knowledge. Their nation lacked the extensive resources, industrial infrastructure, and the necessary time to produce aircraft that matched American standards. The capture of William Roach's P-47 on that November day was not the first encounter of the Luftwaffe with the Thunderbolt in combat. Since April of the same year, when the 4th Fighter Group first escorted B-17 bombers into contested airspace over occupied Europe, German pilots had faced the enormous presence of the Thunderbolt. Initial German combat reports reflected a mixture of both admiration and perplexity. Pilots, accustomed to the agility and nimbleness of aircraft like the Focke-Wulf FW-190 or the Messerschmitt Bf-109, found the American fighter to be unexpectedly cumbersome. It was notably large, seemingly sluggish at lower altitudes, and appeared to have been engineered by designers unaware of the specific demands of aerial combat. For these German pilots, the Thunderbolt seemed to defy the conventional expectations of fighter aircraft. Its sheer size and raw power challenged their preconceptions about what an effective fighter could be in the skies over Europe. The Luftwaffe quickly grasped the significance of their recent encounter with the American P-47 Thunderbolt. Throughout the spring and summer months of 1943, combat reports from German fighter units consistently highlighted certain perceived shortcomings of this formidable aircraft. Pilots observed that the Thunderbolt struggled with a notably slow rate of climb, and that its handling at lower altitudes could be ponderous and unwieldy. Additionally, many German pilots interpreted the American pilot's apparent reluctance to engage in traditional turning dogfights as a sign of vulnerability, leading them to consider the aircraft inferior from their point of view. Initially, seasoned Luftwaffe pilots assessed the P-47 as a design that was fundamentally less capable, especially at medium altitudes, where a majority of the aerial engagements took place. They believed that clever maneuvering and superior German tactics could outwit the Thunderbolt, which they saw primarily as a heavy, somewhat cumbersome fighter. This judgment, however, would prove to be dangerously short-sighted. Yet, amidst these evaluations, some details in the combat reports pointed toward a far darker reality, one that sharply contradicted the notion that the Thunderbolt was merely a lumbering, less capable fighter. German pilots recounted instances where aircraft that chose to disengage from a fight could accelerate into a dive and, once committed, could not be caught by pursuing German fighters. They described the terrifying firepower of the P-47, noting that its 8 heavy machine guns unleashed a devastating curtain of bullets when American pilots decided to fight rather than flee. Furthermore, the reports mentioned that the aircraft's armor appeared to be remarkably resilient, often impervious to the standard German 7.92 mm rounds, and even capable of resisting hits from 20 mm cannons on occasion. Such armor would prove a formidable advantage, allowing the Thunderbolt to absorb damage that would have disabled or destroyed other fighters. Perhaps most disturbingly, German pilots observed that even when a Thunderbolt was hit and badly damaged, missing wings, engines streaming oil, or control surfaces shot away, the aircraft could still limp back to base in England. These damaged fighters often returned with severe battle scars, yet remained under pilot control, still capable of flight despite critical structural losses. This resilience was astonishing and indicated a level of durability that the Luftwaffe had not fully appreciated. The turning point came when Lieutenant Roach's intact P-47 finally made a forced landing at Karpik. The Luftwaffe staff there had the rare opportunity to examine this aircraft in detail, and they recognized at once that capturing a complete, undamaged example could dramatically alter their understanding of its capabilities. The local German personnel quickly realized its potential value for intelligence and evaluation. Acting swiftly, the aircraft was placed under armed guard immediately to prevent any sabotage or damage that could compromise their analysis. The Americans had already taken steps to hide its identity. German markings, specifically the Balkan Crower insignia, were painted over the wings and fuselage, and bright yellow paint was applied to the underside and tail surfaces. This yellow marking, denoted by the Luftwaffe as RLM-04, was standard procedure for captured aircraft used in testing, to prevent friendly fire incidents, especially from the German anti-aircraft defenses, which might otherwise mistakenly shoot down their own evaluation planes. The aircraft was then prepared for transport to Rechlin, the Luftwaffe's premier aeronautical testing station, located approximately 62 miles northwest of Berlin, in the region of Mecklenburg. Once there, it received the designation T9+FK, a code used by the Luftwaffe's renowned evaluation unit, the Zirkis Rosarius. An experienced team was assembled to conduct the initial assessments, led by Hans-Vera Lehre, the chief test pilot and head engineer at the Air Prabang Stella Rechlin facility. Hans-Vera Lehre, who during the war would eventually fly more than 125 different aircraft types, never suffering a crash or serious damage, approached the P-47 with a mixture of professional curiosity and cautious respect. His initial impressions, carefully documented in his logbook and later shared in his memoirs, revealed a pilot impressed by the aircraft's engineering, yet aware of its unfamiliar systems and the need for thorough understanding before drawing conclusions. The examination of the Thunderbolt was set to unlock secrets that could potentially shift the tactical balance in the skies. During his extensive testing period, he documented numerous encounters with the Allied aircraft of the era, gaining a profound appreciation for their design intricacies. When examining the cockpit of the P-47 Thunderbolt, a formidable American fighter from World War II, Lears was struck by its astonishing complexity, a stark contrast to the more streamlined and familiar German fighters he had previously flown. The array of gauges and instruments seemed almost doubled in number compared to German fighters, creating an environment that initially appeared overwhelming. The control panel was filled with an array of strange levers and switches that managed systems entirely different from those in German aircraft. Among these, the turbo supercharger system demanded a deeper understanding of exhaust flow management, a concept that had remained largely theoretical within German aviation circles. In contrast, this was a standard, well-integrated feature of the American design, illustrating a different engineering approach. The propeller system, which operated at a constant speed, was notably distinct from the German equivalents, requiring pilots to adapt to unfamiliar procedures. Perhaps most perplexing was the aircraft's elaborate automatic engine management system. Unlike German fighters, where pilots manually adjusted throttles and mixture controls during flight, the P-47 was equipped with an advanced, supposedly automatic system, whose operation was not immediately transparent. Lears recalled in his memoirs that the cockpit itself could confound even the most seasoned pilots. He admitted that although he gradually deciphered the functions of many levers and instruments, a handful of controls remained obscure, their purposes unclear at first glance. Preparing for flight, he dedicated a considerable amount of time on the ground experimenting with these controls and studying the layout meticulously. This methodical approach to familiarizing himself with an unfamiliar aircraft, without the benefit of detailed pilot manuals or operational guides, underscored his dedication to safe and effective testing. The engine start procedure alone highlighted the aircraft's sophistication, far surpassing typical German practices. The Pratt & Whitney R2800 double Wasp engine was a behemoth, requiring specific, carefully executed steps to properly initialize its complex turbo supercharger system. Lears approached this process with methodical precision, as his engineer's mind carefully catalogued each step, deducing the purpose behind every action. When the massive radial engine finally roared to life, the sound it produced was utterly unlike the sharp bark of German inline engines or even the BMW 801 radial of the Focke-Wulf FW190. Instead, it emitted a deep, resonant rumble, one that suggested enormous displacement and immense power reserves held in reserve. As Lears taxied the aircraft, he felt its weight through the controls, aware of the sheer mass of this fighter. The P-47D weighed nearly 10,000 pounds when empty, and with a substantial fuel load and full ammunition, its weight climbed close to 13,500 pounds. For comparison, the German FW190A8, one of the heaviest single-seat fighters fielded by Luftwaffe, had an empty weight of approximately 7,650 pounds and a maximum loaded weight around 10,800 pounds. The Thunderbolt's size and mass were thus striking. It was genuinely massive for a single-seat fighter, exceeding the dimensions of some twin-engine aircraft in the German Luftwaffe. As Lears advanced the throttle for takeoff, the differences in engineering philosophies between Germany and the United States became immediately apparent. The R2800 engine delivered around 2,000 horsepower at standard boost settings, with emergency war power capable of reaching approximately 2,300 horsepower through water methanol injection. This powerful engine contrasted sharply with the German BMW 801D, which, even at its peak, produced roughly 1,700 to 1,730 horsepower at maximum continuous power. Despite this engine power advantage, the greater weight of the P-47 meant that the takeoff run was longer than expected. Lears noted that the aircraft required a carefully managed acceleration, indicating that the design trade-offs, such as size and weight, had significant operational implications, even for a machine as advanced and potent as the Thunderbolt. The rugged expanses of the grass field at the transfer airfield stretched endlessly in every direction, serving as a stark reminder of the harsh environment in which the aircraft operated. Once airborne, however, the true nature of the P-47 Thunderbolt began to reveal itself to Lurch, challenging prior assumptions and exposing its true potential. It became clear that the German pilots, who had fought against these aircraft mainly at low altitudes, had fundamentally misunderstood the true capabilities and limitations of this formidable machine. As Lurch steadily climbed into the sky, he carefully monitored the turbo supercharger, gradually bringing it up to its optimal operating temperature. With each ascent, the aircraft's performance characteristics shifted perceptibly. Below approximately 15,000 feet, the P-47 felt exactly as German combat pilots had reported in their combat accounts. Heavy, somewhat sluggish in its turns, and noticeably less maneuverable than the nimble fighters the Germans fielded, like the Focke-Wulf 190 or the Messerschmitt Bf 109. In this altitude zone, any competent German pilot flying a modern fighter could easily outmaneuver the Thunderbolt in sustained turning combat, exploiting its sluggishness and relatively mediocre rate of climb. Yet, as Lurch moved above 20,000 feet, the traits of the aircraft changed dramatically. The turbo supercharger, driven by the exhaust gases and becoming more efficient as the ambient air pressure dropped, began forcing large volumes of compressed air into the engine cylinders. While the German engines, which relied on naturally aspirated or limited supercharged systems, struggled to breathe at these heights, losing power and efficiency, the R2800 engine of the Thunderbolt maintained its full rated output. This remarkable feature meant that at elevations around 25,000 feet, where German fighters might operate at roughly 70% of their sea-level power, the Thunderbolt's engine was still delivering its maximum, designed for performance. At this altitude, Lurch advanced the throttle fully forward, feeling a surge of acceleration that was surprisingly vigorous for an aircraft of such considerable size and weight. He rolled into a steep dive, eager to examine its high-speed capabilities firsthand. In response, the aircraft exhibited a level of responsiveness that bordered on the violent, its controls stiffening and the airframe resisting the air's compressive forces. In this aggressive descent, the P-47 accelerated past 500 miles per hour, reaching a velocity where the airflow around the fuselage and wings caused the controls to stiffen significantly. At such speeds, recovering from a dive was a demanding task requiring both hands firmly gripping the control stick and considerable physical strength, an indication of the approaching limits of the aircraft's aerodynamics before compressibility effects fully took hold, a phenomenon that would not be fully understood until the jet age. What struck Lurch most profoundly during these tests was the aircraft's impressive roll rate. Contrary to what many German pilots had presumed about the heavy American fighter, the P-47 was capable of rolling faster than any German aircraft Lurch had previously flown, including the renowned Focke-Wulf 190, an aircraft celebrated for its exceptional roll performance. Despite its considerable size and weight, the Thunderbolt's ability to turn quickly on its axis provided a significant tactical advantage, particularly when combined with its devastating dive speed. This combination allowed an American pilot at high altitude to execute a quick roll inverted and then escape rapidly, diving away from pursuing enemies at speeds that German fighters simply could not match. Any Luftwaffe pilot attempting to pursue an escaping P-47 at high altitude would encounter compressibility effects that compromised the aerodynamically sensitive control surfaces. However, the Thunderbolt's stronger airframe and more powerful controls managed these effects far more effectively, enabling the American pilot to maintain better control even at extreme speeds. Lurch methodically flew the captured Thunderbolt through an extensive program of flight tests, systematically exploring its full flight envelope in accordance with standard evaluation procedures. These tests aimed to yield comprehensive data about the aircraft's performance capabilities and limitations. His preliminary report included observations that caused concern among Luftwaffe leadership, who still harbored the belief that German fighter designs were superior and fundamentally unchallenged by their adversaries. The data emerging from these tests suggested otherwise, that the American Thunderbolt had capabilities that exceeded expectations and could counter or surpass many features of German fighters. This realization glaringly highlighted the shifting balance of aerial power, forcing a reassessment of tactics and designs based on newfound insights into the true prowess of the P-47 Thunderbolt. The P-47 Thunderbolt, operating at altitudes exceeding 25,000 feet, found itself in a strategic environment where aerial combat was progressively shifting higher, as Allied bomber formations ascended to escape the relentless German anti-aircraft fire. At these elevated levels, the Thunderbolt was not simply on par with German fighters. In many respects, it outperformed them. It boasted specific, vital advantages that effectively neutralized the German fighters' customary strengths in maneuverability and rate of climb. In the aftermath of these encounters, the engineers at Reikland's workshop dedicated themselves to meticulous and exhaustive testing of the aircraft's critical components. This process adhered strictly to the rigorous standards established by AEROB, an authoritative body renowned for its precise evaluation protocols. Every part of Beetle, the aircraft's nickname, was scrutinized in detail. Photographs were taken from multiple angles to capture every nuance of its construction. Each dimension was measured with high-precision instruments, ensuring every numerical detail was accurate. The project also involved weighing every major component and assembly, to assess weight distribution and overall balance. Systematic testing under various environmental and operational conditions was conducted to understand performance limits and durability. Particular focus was paid to the turbo supercharger system, which represented the technological frontier distinguishing American aircraft from their German counterparts in high-altitude performance capabilities. The engineers' investigative efforts unveiled startling details that challenged preconceived notions rooted in resource-constrained design philosophies typical of late-war German aviation development. The core of the American power plant was the Pratt & Whitney R2800 double WASP engine, a marvel of engineering comprising 18 cylinders arranged in 2 rows of 9, symmetrically encircling a central crankshaft. This engine boasted a total displacement of 2,845 cubic inches, equivalent to nearly 45.958 liters. A figure that, at first glance, might seem comparable to the German BMW 801D. The latter displaced approximately 2,560 cubic inches, or about 41.8 liters. However, displacement alone did not account for the noticeably greater power generated by the R2800. Constructed with forged aluminum alloy pistons, equipped with sodium-cooled exhaust valves designed to endure the severe thermal stresses of high-output operation, and driven by a forged, high-grade steel crankshaft, the Pratt & Whitney engine was a marvel of material science. German metallurgists, inspecting the engine in detail, regarded it with a mixture of admiration and envy, recognizing that American manufacturers had secured materials no longer readily available to them in sufficient quantities. The craftsmanship and material quality of each component left the German inspection team utterly amazed. Every component was manufactured with astonishing precision, adhering to tolerances so tight that the surface finishes across all parts remained uniformly smooth. The magnetos, crucial for ignition, incorporated materials that had become increasingly rare in Germany, a clear testament to American resourcefulness. The spark plugs employed high-grade ceramic insulators superior in quality to their German counterparts, and the fuel injection system operated with a level of precision typically reserved for laboratory equipment, rather than the harsh realities of combat aircraft. Most significantly, the entire engine displayed no signs of material substitution or downgrading, no compromises stemming from resource shortages or wartime improvisation. It was built exactly as originally designed, using all specified materials and construction techniques. This meticulous adherence to quality contrasted sharply with the late-war German manufacturing approach, which was increasingly marked by makeshift solutions and resource difficulties. The turbo supercharger system illustrated the extent of American engineering sophistication. Exhaust gases from all 18 cylinders were collected through a network of manifolds, routed via insulated pipes that extended along each side of the fuselage. These pipes directed the hot exhaust into a turbine unit located behind and below the cockpit. This turbine, spinning at incredible speeds, was driven by the high-temperature exhaust gases, which in turn powered a centrifugal compressor, an integral component designed to increase the intake air pressure at high altitudes. This entire setup exemplified American ingenuity in high-altitude engine performance, representing a technological leap that the Germans had attempted to replicate but had never perfected in subsequent production aircraft. The complexity and precision of this turbo supercharger system were unmatched, underscoring the superior engineering that allowed the Thunderbolt to operate effectively at altitudes where German aircraft typically struggled to maintain performance. By the mid-1940s, the development of aircraft engine supercharging systems had reached remarkable levels, exemplified by the American approach, which incorporated an auxiliary component known as a turbo supercharger. This device was designed to force extra air into the engine's intake, significantly enhancing power output at high altitudes. The system was carefully integrated with an intercooler, an essential component that served to cool the compressed air after it passed through the supercharger. Lowering the temperature of this intake air increased its density, thereby allowing the engine to produce more power, and reducing the risk of harmful engine knocking or detonation, which could cause catastrophic engine failure. The entire system was governed by sophisticated automatic regulators that meticulously maintained the boost pressure and the turbine speed. These controls operated seamlessly, requiring minimal intervention from the pilot beyond initially setting the desired manifold pressure, ensuring optimal engine performance under varying flight conditions. The Germans, renowned for their engineering prowess and theoretical understanding of aeronautical systems, had conducted comprehensive experimental programs exploring similar concepts for boosting engine performance at altitude. Yet, despite their thorough research, the practical challenges of translating these advanced ideas into mass-produced combat aircraft proved to be insurmountable within the constraints of German wartime industry. By the year of 1943, German engineers faced formidable material shortages and manufacturing limitations that greatly hindered their ability to produce such complex systems at scale. Implementing a turbo supercharger required materials capable of withstanding extreme thermal stresses, chiefly exotic high-temperature alloys for turbine blades that had to endure continuous operation at blistering speeds and temperatures. The control mechanisms for these systems necessitated a level of manufacturing precision and component reliability that was difficult to achieve consistently, especially when scaled up for mass production. The extensive ducting and piping involved demanded heat-resistant materials and airtight seals capable of maintaining their integrity despite vibrations, temperature fluctuations, and the risk of battle damage. Operating reliably under combat conditions posed additional challenges. Components needed to function flawlessly amidst constant vibrations, rapid temperature swings, ranging from nearly -60°F at high altitude to over 200°F near the engine, and the shock of potential battle damage. American industry had succeeded in overcoming each of these hurdles, producing and installing entire turbo supercharger systems as standard equipment on every P-47 Thunderbolt aircraft they built. Such integration was not limited to experimental models or specialized missions. Instead, it became a fundamental aspect of the aircraft's design. The turbo supercharger was so seamlessly incorporated that it became a standard feature in thousands of P-47s, demonstrating a level of industrial capability and technological mastery that German engineers found difficult to fully grasp or replicate during the same period. Correspondence from German technical assessments, such as those documented during the Recon evaluation, highlighted that the turbo supercharger system alone represented a pinnacle of engineering sophistication. The materials used, the precision manufacturing processes, and the rigorous quality control measures required to produce such reliable components at scale far exceeded what German industry could achieve at that time. This was especially true given the strategic scarcity of vital materials, the progressive decline in manufacturing standards due to Allied aerial bombing campaigns, and the substitution of skilled German workers with forced labor, all of which severely hampered production capabilities in the later years of the war. In addition to propulsion systems, the aircraft's armament configuration further exemplified American resourcefulness and meticulous attention to design detail. The P-47D Thunderbolt was outfitted with a total of 8 Browning M2 machine guns, each caliber 50 caliber, mounted in a balanced and highly effective arrangement with 4 guns in each wing. Compared to most German fighters of the same era, which typically carried a mixed armament of 4 machine guns alongside 2 20mm cannons or, in some early models, only 6 machine guns, the American design showcased a deliberate choice to prioritize heavy firepower. The decision to install such a formidable complement of machine guns was driven by a strategic desire to maximize the aircraft's destructive potential, even if this meant adding weight and increasing mechanical complexity. Each of the 8 guns drew its ammunition from a dedicated box built directly into the wing structure, ensuring a steady supply during combat. These ammunition boxes each contained approximately 425 rounds, summing to a total capacity of over 3,400 rounds for the entire aircraft. This substantial ammunition load, combined with the high rate of fire and the sheer number of guns, provided the P-47 with a significant advantage in aerial combat, allowing it to deliver a relentless barrage of firepower that could intimidate and disable enemy fighters more effectively than many of its contemporaries. The armament of the P-47 Thunderbolt showcased a remarkable combination of firepower, engineering precision, and durability that set it apart from many contemporaries. When comparing it directly to the famed Focke-Wulf FW190A, one finds that the latter was typically equipped with approximately 2,000 rounds of ammunition spread across its machine guns, along with around 500 rounds for its cannons. In contrast, the P-47's 8.50 caliber machine guns could sustain continuous firing, allowing a pilot to unleash a relentless barrage for roughly 20 seconds before the ammunition supply was fully depleted. This firing capability meant that, At the combined rate approaching 100 rounds per second, the pilot could effectively lay down a hail of destructive fire that was difficult for any adversary to withstand. When all 8 guns were correctly synchronized and precisely aimed so that their streams of projectiles converged on a single point in space, the volume of lead and explosive force was simply overwhelming. Such a concentrated burst could, and often did, devastate enemy aircraft or ground targets in a matter of seconds. This capability was not just theoretical. German test teams, after capturing and examining the aircraft's armament system, documented its powerful effects in vivid detail. The technical excellence of the installation left a strong impression on German armament specialists, who noted the robustness and meticulous engineering of the system. Each of these guns was housed within an electrically heated bay to prevent freezing at extreme altitudes, where temperatures could plummet to -60°F or lower. Special care was taken to manage the ejection of spent cartridge cases and the disintegrating links of belt-fed ammunition. These were channeled through chutes and expelled via ports located on the lower surface of the wing. This design feature ensured that the empty cartridges did not jeopardize the aircraft's aerodynamics or interfere with the operation of control surfaces, thus maintaining the aircraft's structural integrity and maneuverability. Remarkably, the firing tests conducted during the VLAN trials demonstrated flawless performance under a wide range of atmospheric conditions. The system successfully fired thousands of rounds without any jamming or feed malfunctions, underscoring the high reliability of American manufacturing standards. Furthermore, the quality of the ammunition itself revealed another critical strength of American industry. The .50 caliber rounds, which included armor-piercing cores, incendiary compounds, and tracer elements, were produced consistently to exact specifications. The armor-piercing cores reliably penetrated enemy targets, the incendiary components functioned as intended, and the tracers burned predictably, providing excellent visibility for gunners. Testing further confirmed that American ammunition was generally more dependable than its German counterparts, especially as the war progressed and resource shortages began to affect manufacturing quality. Unlike German rounds, which saw a decline in consistency due to the scarcity of strategic materials, U.S. ammunition maintained high reliability. The Thunderbolt's armor protection exemplified the American strategic approach, accepting substantial weight penalties in exchange for increased pilot survivability. This philosophy starkly contrasted with German priorities, which favored lighter aircraft and performance, often at the expense of comprehensive protection. The cockpit of the P-47 was heavily fortified with armor plates on multiple sides, creating what American designers called an armored bathtub. This reinforced structure provided critical protection from below and behind, shielding the pilot from enemy fire and shrapnel. The windscreen was constructed from thick, bulletproof glass capable of stopping machine gun rounds and resisting fragments from cannon shells. Additional armor plates safeguarded vital systems such as the oil coolers and the vulnerable turbo supercharger, ensuring these components could withstand damage during combat. The total weight of the armor exceeded 200 pounds, roughly equivalent to adding 2 more machine guns along with their ammunition load, further illustrating the value placed on pilot survivability. In comparison, German fighters generally carried less extensive armor, prioritizing lighter airframes to achieve better speed and agility. This design choice often resulted in higher casualties among pilots, as the aircraft offered less protection. The fundamental difference between the American and German philosophies was clear. The U.S. considered pilot survivability at least as important as raw performance, while the Germans favored lightweight, high-performance aircraft that left their pilots more exposed. This difference extended beyond armor and into maintenance philosophy. American designers anticipated that mechanics working at forward air bases, often under challenging conditions, including nighttime, bad weather, or with enemy threats nearby, needed to perform repairs and servicing swiftly and efficiently. To facilitate this, the aircraft was designed with large access panels on major components, all secured with accessible fastening systems, allowing for quick repairs and replacements in the field without extensive effort or specialized tools. The design of the American aircraft incorporated quick-release fasteners that could be operated with only basic tools, making routine maintenance and repairs significantly more straightforward. When necessary, the massive engine could be swapped out in the field within a matter of hours, provided that standard hoisting equipment was available and that maintainers followed clearly documented procedures, an approach that prioritized simplicity and efficiency. In contrast, German fighters, crafted with the expectation of factory-level maintenance for major repairs, typically required more extensive disassembly to access and service critical components. This difference in design philosophy reflected broader disparities in resource availability. Americans, benefiting from abundant industrial capacity, invested in creating machines that emphasized ease of maintenance and operational readiness. German aircraft, on the other hand, often prioritized initial performance and durability but lacked the same degree of maintainability, especially as resource shortages and strategic bombing campaigns increasingly hampered their industrial output. This divergence also extended to onboard communication technology, where American advancements once again surpassed their German counterparts. The radio systems installed in captured fort fighters exemplified this superiority. These aircraft were equipped with an SCR-274N command radio, capable of reliable air-to-air and air-to-ground communications, as well as an SCR-515A liaison radio that provided additional channels. These radios operated with clearer audio quality and over longer distances compared to the German radio systems of the time, which were plagued by persistent interference problems. American engineers had apparently addressed these issues through superior component design, using better shielding and more reliable electronic parts, resulting in communication systems that held up better under combat conditions. Furthermore, the American aircraft's radios were integrated with an identification friend or foe (IFF) system, a sophisticated feature that automatically distinguished Allied aircraft from enemy ones. This automated identification played a crucial role in preventing friendly fire incidents and reflected a level of technological advancement that the Germans lacked in 1943. The German forces, at that stage of the war, had not yet developed or integrated such automated systems into their aircraft, exemplifying the technological gap that widened as the conflict progressed. What was perhaps most striking to German engineers upon examining the captured P-47 was not any single advanced system but rather the overall impression of exceptional quality and completeness displayed throughout the aircraft. Every component seemed to be the optimum version that American engineers could conceive and manufacturers could produce, indicating meticulous attention to detail and a rigorous standard of manufacturing fidelity. There was no evidence of corners cut or materials replaced due to shortages. Nothing suggested that future or substitute components had been used because their preferred materials were unavailable. Instead, the aircraft reflected an unwavering commitment to maintaining the integrity of the original design specifications, even in the face of wartime hardships. This high level of manufacturing precision and adherence to original plans was becoming increasingly difficult for German industry to sustain as the war dragged on. The ongoing flight testing program, which continued through the winter of 1943 and into early 1944, involved the assessment of additional captured P-47s at the Recklan testing facilities. These evaluations aimed to compare German-produced aircraft with American standards, an effort to understand the technological gaps and weaknesses. The significance of this point was underscored by the event on May 29, 1944, when another American P-47 fell into German hands. This incident occurred when 2nd Lieutenant Lloyd S. Hathcock of the 3001st Fighter Squadron, part of the 332nd Fighter Group, became disoriented during a mission. His aircraft, capturing its pilot's distress, ultimately ended up in German possession, providing yet another opportunity for the Germans to analyze firsthand the craftsmanship, technological sophistication, and maintenance philosophy underpinning the American warplane design. During a routine ferry flight that unexpectedly turned into a navigational error, an American aircraft inadvertently landed at the heavily fortified enemy-held airfield of Rome Littorio in Italy. The aircraft, identified by the serial number 427591, was swiftly seized by German forces upon its arrival. This fighter was a Republic P-47 Thunderbolt, a rugged and formidable aircraft that had previously served as the personal mount of the renowned American ace, George Notney, who had achieved a total of 8 confirmed aerial victories while flying with the 317th Fighter Squadron. Following its capture, the Germans transferred the aircraft to their testing and evaluation facilities, initially assigning it the designation 8+6. Later, on October 12, in the year of 1944, the aircraft was moved to the Zirkis Rosarius unit, an elite testing squadron dedicated to analyzing captured Allied aircraft. It was then given the new designation T9+LK. The data and insights obtained from the extensive testing at Recklan contributed significantly to tactical assessments, leading to recommendations that were formally distributed to the frontline Luftwaffe fighter units. These tactical advisories emphasized that engaging P-47 Thunderbolts below 15,000 feet offered the highest likelihood of success for German pilots. This recommendation stemmed from the P-47's relatively poor performance at low altitudes and its sluggish rate of climb, which put German fighters at a clear advantage in that altitude regime. German pilots were specifically cautioned against attempting to disengage by diving away from attacking Thunderbolts, as the American fighters' ability to accelerate rapidly in a dive rendered such tactics futile. The Thunderbolt was capable of reaching speeds that German aircraft could not match once they dove. The reports also noted that even damaged P-47s could often continue flying and pose a threat to attacking fighters, despite sustaining battle damage that would have incapacitated lesser aircraft. Consequently, German pilots were advised to press their attacks with concentrated firepower, recognizing that a few hits were often insufficient to bring down a Thunderbolt. Instead, relentless and aggressive assaults were required to overcome the aircraft's robustness. However, while these tactical recommendations proved valuable for individual pilots facing the enemy in combat, they could not fully address the broader strategic difficulties faced by Germany. As the war progressed, it became increasingly clear that Germany was confronted by an opponent with virtually unlimited material resources, especially when contrasted with German industrial and logistical capacity. Every P-47 that was damaged or destroyed in combat was swiftly replaced. American production at its most prolific surpassed 300 aircraft per month, ensuring a continuous flow of new fighters. American pilot training programs emphasized producing highly skilled aviators in large numbers, a strategy that Germany found increasingly difficult to counter. Meanwhile, American fighters benefited from a logistical system that efficiently supplied fuel, ammunition, and spare parts without significant disruption. In stark contrast, German logistics suffered under relentless Allied air assaults, which severely degraded supply lines and hindered maintenance and replenishment efforts. The captured P-47 Thunderbolts did not remain solely in evaluation hangars for long. They were eventually transferred to Wunderkreuz Rosarius, a specialized Luftwaffe demonstration unit commanded by Flugkapitän Theodor Rosarius. This elite unit traveled extensively across occupied Europe, visiting frontline fighter bases to showcase the capabilities of captured Allied aircraft to German pilots. These demonstrations served a dual purpose, providing training and insight into enemy aircraft characteristics while also serving as a psychological tool. During these sessions, German pilots could observe firsthand the physical features and tactical nuances of the enemy aircraft they were likely to encounter in combat. Moreover, these demonstrations made it evident that Allied equipment often possessed certain superior capabilities, especially at high altitudes where aerial engagements increasingly took place. Witnessing the performance of the P-47 in action reinforced the understanding that the Allies had technological and engineering advantages that could not be simply countered through tactical adjustments. Post-war interviews with Luftwaffe pilots who attended these demonstrations revealed the profound psychological impact of viewing the captured aircraft. Seeing the enemy's technology up close, recognizing its strengths, and understanding its vulnerabilities left a lasting impression on these pilots, shaping their perceptions of the adversary and influencing their combat strategies in the final phases of the war. The combat performance of American fighters during the conflict was vividly demonstrated through direct confrontations and detailed operational assessments. While pilots of the Zirkis Razarius could attest that German fighters maintained certain advantages in specific flight regimes, particularly at medium altitudes, the clear lessons from combat and intelligence data revealed a different story at the altitudes where American bomber formations, escorted by P-47 Thunderbolts and later P-51 Mustangs, typically operated. At these higher elevations, German fighters found themselves at a significant disadvantage, revealing a gap that became ever more evident as the war progressed. Intelligence obtained from captured P-47 aircraft dispelled some of the more optimistic assumptions that had once circulated within Luftwaffe briefings at the start of the conflict. These captured planes, subjected to detailed performance testing, showed that at sea level, the P-47D Thunderbolt reached a maximum speed of roughly 350 miles per hour. While respectable, this speed was not particularly impressive when compared to the FW-190A, which could attain approximately 408 miles per hour at the same altitude. Such data challenged earlier beliefs that American fighters had a clear speed advantage across all flight regimes. As the aircraft climbed to 10,000 feet, the P-47's velocity increased to about 375 miles per hour, demonstrating improved performance at higher altitudes. However, it was at 30,000 feet that the Thunderbolt truly outshined many of its German counterparts, reaching a speed of around 426 miles per hour. In stark contrast, the FW-190A struggled to push beyond 370 miles per hour, and the Bf-109G, another primary German fighter, managed only roughly 385 miles per hour at the same altitude. This data underscored a definitive, growing combat advantage for American fighters at high altitudes, an advantage that became increasingly critical as Allied bombers ascended to higher elevations in an effort to evade German anti-aircraft artillery and fighter interception. The comparison of service ceilings further reinforced the disparity. The P-47 Thunderbolt could operate effectively up to an altitude of approximately 42,000 feet, a level at which German fighters rarely maintained effective engagement. German fighters typically struggled above 35,000 feet, with their performance declining sharply due to the reduced power output of their engines in the rarefied, thin atmosphere. Consequently, American bomber formations, which frequently operated at these higher altitudes, were often beyond the reach of their German counterparts. When German fighters did attempt to intercept, they often faced the limitations of their aircraft's reduced maneuverability and insufficient fuel reserves, making effective combat maneuvering at such heights nearly impossible. In terms of operational range, the Americans once again demonstrated a significant advantage rooted in their industrial capacity and logistical planning. The P-47D, when fitted with external fuel tanks, could escort bomber missions deep into enemy territory, sometimes extending missions over 1,000 miles or more. Early models of the Thunderbolt, with limited internal fuel capacity, had been somewhat restricted. However, by the year of 1944, these aircraft were routinely equipped with 108 drop tanks, allowing them to undertake long-range missions without difficulty. In comparison, German fighters, primarily designed for short-range interception and defensive operations within the Reich's interior, lacked the internal fuel capacity necessary for extended sorties. This operational limitation meant that American fighters could choose their engagement times and locations at their convenience, while German fighters were often confined to defensive roles, fighting from a positional disadvantage. Further insights into American aerial tactics and pilot training emerged from examining the gun camera footage and analyzing the damage patterns on aircraft that had survived combat before being captured. These analyses indicated that American pilots consistently employed tactics optimized to leverage the strengths of the P-47, focusing on high-altitude combat where its turbo-supercharged engine provided a decisive advantage. They deliberately maintained altitude to maximize their performance, exploiting speed and firepower while carefully avoiding situations that would expose the aircraft's vulnerabilities, such as close-range dogfights against more agile German fighters at lower altitudes. Overall, the captured aircraft and the wealth of operational data provided compelling evidence of the American fighter's strategic edge in both range, altitude, and speed. This advantage greatly contributed to the Allies' ability to protect their bombers on deep penetration missions into Germany, establishing a clear dominance in the air and shaping the course of aerial combat throughout the latter part of the war. During the course of aerial combat, American fighters strategically opted to employ dive and zoom attack techniques rather than engaging in prolonged dogfights characterized by tight, turning battles, where the German fighters traditionally held the advantage. Instead of risking close-range, individual confrontations, American pilots coordinated their efforts either in pairs or in formations of 4 aircraft, working seamlessly together to maximize mutual support. This approach often meant deliberately passing up seemingly favorable opportunities for solo engagement if it compromised their cohesion or tactical integrity. The discipline and precision with which American pilots executed this coordinated combat methodology left a strong impression on Luftwaffe analysts who meticulously studied the available evidence. Many experienced German aces, accustomed to relying on their personal skill, aggressive tactics, and individual daring to secure victory, found themselves increasingly outmatched by this systematic and disciplined American approach. Unlike the German pilots, who often depended on personal initiative, American aviators adhered rigidly to established tactical doctrines. They maintained tight formations, supported each other relentlessly, and avoided allowing personal pride or impulsiveness to disrupt their carefully planned operations. This consistency in tactical execution significantly contributed to the Allies' aerial superiority. This disciplined fighting style, when combined with technological advantages, particularly sophisticated equipment suited for high-altitude combat, and a growing numerical superiority on the Allied side, created a formidable challenge for even Germany's most seasoned pilots. As the war advanced toward the decisive D-Day invasion in June of 1944, the overall strategic situation had deteriorated markedly. Intelligence gleaned from captured aircraft proved increasingly less valuable for Germany's war efforts, as the technological and operational gap between the Axis and Allied air forces widened. The Luftwaffe commanders recognized acutely that Allied aircraft were superior in several critical aspects. They understood well the American tactical doctrines and had extensive technical data on the performance capabilities of Allied planes. Nonetheless, possessing this knowledge alone was insufficient. Germany lacked the necessary resources, strategic materials, manufacturing capacity, and well-trained personnel to mount an effective counteroffensive. The detailed Recon reports, which were diligently compiled and professionally disseminated throughout Germany's Luftwaffe technical services, served primarily as documentation of the widening technological and industrial chasm that was inexorably pushing Germany toward inevitable defeat. A striking illustration of this disparity could be seen in comparing engine production figures. By the end of the war, the American company Pratt & Whitney, together with Leon C. Ford Motor Company, had produced more than 125,000 R-2800 engines. This output alone vastly exceeded Germany's entire wartime combat aircraft engine production. In contrast, BMW produced around 61,000 units of the 801 radial engine over the entire duration of the conflict, while Germany's most prolific inline engine, the Daimler-Benz DB605, totaled approximately 42,400 units. American industry's capacity to produce advanced aircraft engines was so vast that their output of a single engine type surpassed Germany's total combined production of all aircraft engines used during the war. Furthermore, American aircraft manufacturing during 1944 reached staggering levels, with roughly 96,000 aircraft produced in that year alone. In comparison, Germany's total aircraft production for all types during the same period was approximately 25,000. The United States manufactured 38,000 fighters, in addition to 16,000 heavy bombers, along with numerous medium bombers, transport aircraft, and training planes. When factoring in the combined production efforts of Britain and the Soviet Union, the Allies' aircraft output surpassed Germany's by a ratio of more than 5-to-1 by the year 1944. The scope of the industrial infrastructure supporting this immense manufacturing effort was unmatched by Germany's capabilities. For instance, the Aluminum Company of America produced more aluminum in a single year than Germany's entire aluminum industry could generate in its entire wartime history. Similarly, the steel production capacity of the United States vastly outstripped that of Germany, highlighting the profound disparity in industrial strength that underpinned the Allies' operational dominance in the air war. In summary, the Allied forces' strategic use of disciplined tactics, combined with their technological superiority and overwhelming industrial capacity, created insurmountable obstacles for German fighters, who found themselves increasingly outnumbered, outproduced, and outmatched as the relentless gears of modern war turned inexorably in favor of the Allies. Throughout the war, American industry consistently outperformed expectations, often surpassing the combined output of entire regions dedicated to military manufacturing. The industrial capacity of the United States was so vast that it could produce not only the volume of equipment needed for its own forces but also supply substantial quantities to its allies in Britain and the Soviet Union. In the realm of aircraft production, American factories operated with remarkable efficiency. The assembly lines used for manufacturing vehicles, especially in the automotive sector, relied heavily on batch production methods, a practice that German plants also employed but without the same scale or speed. The machine tools that built the components of aircraft, machines that in turn assembled the aircraft, were themselves mass-produced, ensuring that American industries could meet enormous demands without delay. This comprehensive manufacturing effort allowed the Allies to maintain a steady supply of aircraft and weapons, ultimately giving them a significant strategic advantage. The fate of some aircraft, such as the P-47 Thunderbolts, reflects the extensive air war in Europe. These aircraft, after their service in active combat, often found themselves in the chaotic final months of the European conflict, sometimes ending their operational life among captured enemy equipment. One notable example is an aircraft designated T9+FK, originally known as William Roach's Beetle, which was recovered by American forces in May of the year 1945 at Göttingen. It was discovered amid a collection of captured Allied aircraft, which the Germans had been scrutinizing and evaluating as part of their efforts to understand and counter Allied technology. Photographs taken by American troops depict this particular aircraft still bearing remnants of German markings, parked alongside Focke-Wulf FW-190s and Messerschmitt Bf-109s. These photographs effectively serve as a visual record of the Germans' extensive intelligence-gathering operations, documenting the breadth of their efforts to analyze captured equipment. The Thunderbolts used by German evaluation units provided German pilots and engineers with a vital education, insights into American aircraft design, that they desperately needed. Unfortunately, for the Germans, this knowledge arrived too late to influence the strategic course of the war significantly. These aircraft exemplified a fundamental aspect of American industrial philosophy, a focus on absolute capability rather than sleek elegance or resource efficiency. The United States prioritized building systems with abundant resources, emphasizing systematically producing a material advantage over individual technical perfection. When combined with near-limitless manufacturing capacity, this approach resulted in weapons systems that, overall, outclassed their German counterparts, despite instances where German designs might have showcased superior features in particular isolated parameters. This lesson extended far beyond the P-47 Thunderbolt itself. Every category of captured American equipment echoed the same core story. For example, the Boeing B-17 Flying Fortress, with its quartet of turbo-supercharged engines, embodied a strategic bombing capability that Germany had been unable to develop effectively. Similarly, the iconic P-51 Mustang, famous for its aerodynamic airframe combined with the British-made Rolls-Royce Merlin engine, has been widely regarded by many historians as the finest piston engine fighter of the entire war. Its design exemplified the seamless integration of American engineering with British technological support, creating a fighter aircraft that set new standards. The P-38 Lightning also demonstrated American ingenuity and willingness to pursue unconventional solutions. Its twin-turbo supercharged engines and tricycle landing gear reflected a departure from traditional aircraft design, emphasizing innovation and versatility. These aircraft types revealed consistent themes in American military manufacturing. Problems were addressed primarily through superior engineering solutions, supported by the vast industrial infrastructure that allowed for mass production, rather than through resource conservation or painstaking optimization constrained by scarcity. Luftwaffe analysts recognized that their defeats weren't primarily due to tactical failures or inferior pilot training. Although the Germans trained their pilots adequately, they observed that they were being systematically outproduced and out-engineered by an industrial system capable of designing effective equipment and producing it in staggering quantities. American industrial might rendered many of German technical advantages increasingly irrelevant on the battlefield. This capacity enabled the United States to develop and mass-produce aircraft and other systems that, in aggregate, outperformed their German counterparts, an outcome that proved decisive in the ultimate outcome of the air war. In essence, the American approach was characterized by solving complex problems through engineering excellence bolstered by unmatched industrial capacity, rather than relying solely on the optimization of resources or tactical ingenuity. This strategy not only changed the nature of wartime production but also redefined the very standards of technological dominance in modern warfare. By the year of 1943, the industrial powers of the world had harnessed their vast manufacturing capabilities, sourcing abundant raw materials and establishing highly efficient logistics systems to sustain their war efforts. These factors contributed significantly to the strategic advantages held by certain nations, most notably Germany, which, despite facing crippling limitations on its industrial capacity, endeavored to compensate through ingenuity and innovative engineering. German engineers and designers worked tirelessly to extract maximum performance from their limited resources, attempting to achieve through clever design what their industrial base could no longer support in terms of sheer volume. Throughout the Luftwaffe's technical branches, the implications of this strategy were thoroughly analyzed and documented, emphasizing the importance of technological edge as a means of maintaining parity or superiority on the battlefield. By the end of 1943, Germany had entered the ongoing global conflict with arguably the most advanced air force in the world at that time. Their aircraft were generally superior in performance to those of their adversaries when compared on a one-to-one basis, and German pilots were often better trained than many of their opponents in the early phases of the war. The tactical doctrines employed by the Luftwaffe also demonstrated a higher level of refinement, allowing German pilots to utilize their aircraft more effectively. However, this edge was increasingly undermined by the fundamental limitations of Germany's industrial capacity. Despite efforts to boost aircraft production, the industrial system could not sustain the pace necessary to maintain or expand these advantages in the face of growing opposition. Meanwhile, the United States aircraft industry grew exponentially, with production levels doubling multiple times, specifically in 1940, 1941, and 1942, until by 1944, American factories were churning out over 96,000 aircraft annually. In stark contrast, Germany's annual aircraft output never exceeded 38,000 units, despite relentless and desperate attempts to ramp up production. This discrepancy in industrial capacity was reflected in the widening quality gap between American and German aircraft, which steadily grew over the course of the war. While German aircraft in 1942 were often superior to their American counterparts in terms of design and performance, by 1944, American aircraft had caught up and even surpassed their German counterparts in nearly every critical category. By the year of 1945, the disparity between the two nations' aircraft had become a vast chasm, fundamentally shifting the balance of air power. The American fighters, such as the P-51H and P-47N, exemplified the evolutionary refinement of already outstanding designs, benefiting from continuous technological improvements and lessons learned throughout the war. In contrast, German fighters like the TAR-152 were desperate attempts to squeeze more performance out of their increasingly compromised industrial systems, which were under relentless assault from strategic bombing campaigns, experiencing shortages of raw materials, and suffering from the loss of skilled workers who had been replaced by poorly trained forced labor. The psychological toll on the Luftwaffe's morale was profound, as the endless influx of capable enemy aircraft became as damaging as material losses. German pilots often reported feeling less like noble warriors engaged in honorable combat and more like targets actively subjected to a systematic campaign of destruction. Despite managing to shoot down numerous Allied aircraft, the overwhelming and continual appearance of new fighters eroded their confidence. The squadron's esprit de corps diminished as the realization took hold that no matter how skillfully they fought, they were increasingly outnumbered. The sheer numerical superiority of American forces, combined with their relentless attrition strategy, ultimately led to dominance in the skies. The knowledge among German pilots that their equipment was frequently inferior, even if sometimes more advanced in design, was reinforced by the reality of larger quantities arriving daily, supported by superior logistics, and flown by adequately trained pilots who could be replaced swiftly when killed or shot down. This cumulative understanding fostered a pervasive sense of unavoidable defeat within German fighter units during the year of 1944. Captured aircraft like the P-47 Thunderbolt became tangible, irrefutable evidence of this stark reality. These aircraft were not the subject of propaganda or exaggerated intelligence reports. They were genuine machines, available for direct inspection by German pilots and engineers. The Thunderbolt was not a miraculous weapon or a revolutionary technological milestone. Rather, it represented a very good fighter aircraft, meticulously designed and well suited for its intended role. Manufactured in vast quantities, these aircraft were the product of a robust industrial process, ensuring that their performance and reliability remained consistent. The P-47's reputation was based on solid engineering and proven combat effectiveness, which underscored the disparity not only in numbers but also in quality and industrial capacity between the opposing sides. The realization that such a formidable aircraft was simply a product of excellent design and mass production, rather than a radical technological breakthrough, highlighted the importance of industrial strength in modern warfare and demonstrated how numerical and logistical advantages could decisively influence the outcome of the aerial battles during the final years of the war. Power, extensive armament, appropriate levels of protection, and manufacturing in sufficient quantities to overwhelm their adversaries through the systematic deployment of material superiority. This narrative reveals that, despite their thorough understanding and meticulous documentation, the Germans could never translate their knowledge into effective application. The essential reason for this disconnect was that, although they comprehended the capabilities of aircraft like the P-47 Thunderbolt, they lacked the fundamental industrial resources necessary to produce machines of comparable quality and quantity. Critical materials such as aluminum, steel, and fuel, alongside skilled labor, remained scarce, and even the most detailed technical insights could not compensate for the absence of undamaged factories and well-functioning transportation networks vital for large-scale manufacturing. Having precise knowledge of the P-47's technical specifications did not automatically grant access to the high-temperature alloys, advanced manufacturing equipment, stringent quality control systems, or a trained workforce required to reproduce the turbo supercharger systems that made these aircraft so formidable. Even the intelligence derived from captured aircraft, which documented their dimensions, performance, and design features with meticulous precision, ultimately revealed a more sobering reality. This information illustrated Germany's looming defeat in stark detail but offered no realistic pathway to alter the inevitable outcome. It was a clear reminder that mastering intelligence and understanding an opponent's technology was insufficient without the industrial capacity necessary to act on that knowledge. When Allied forces advanced into Germany and seized the Rechlin plant and its associated facilities in May of 1945, They uncovered extensive documentation related to the aircraft evaluation programs that the Germans had carried out throughout the war. The German technical reports, meticulously compiled and stored in countless filing cabinets, detailed every measurable aspect of both American and British aircraft examined during the conflict. These reports exemplified technical thoroughness and scientific precision, embodying thousands of man-hours spent in rigorous measurement and analysis. Despite the depth of this documentation, it represented capabilities that Germany could observe and analyze, but could not replicate due to their increasingly faltering industrial base. Post-war American technical intelligence teams who scrutinized these German reports recognized a striking fact: German engineers had a more precise and comprehensive understanding of American aircraft capabilities than many American military commanders possessed themselves. These insights revealed weaknesses in American designs that American pilots learned to exploit through practical experience and tactical adjustments. Interestingly, the Germans' evaluations of aircraft like the P-47 Thunderbolt were often more detailed and exacting than the American assessments of their own equipment, reflecting Germany's high level of engineering competence, a fact that was never in doubt. However, these reports also implicitly exposed the broader strategic challenges faced by Germany. Despite their engineering prowess and early wartime successes, thanks to excellent pilot training, tactical ingenuity, and innovative tactics, they had embarked on a modern industrial war with an insufficient industrial infrastructure. While their technical expertise and tactical adaptability allowed them to sustain early victories against opponents with similar resource limitations, these advantages proved inadequate against the overwhelming industrial might of the United States. The sheer scale of American industrial capacity, which far exceeded that of all other major powers combined, meant that no matter how advanced their engineering or how skilled their pilots, Germany could only delay the inevitable outcome of their struggle. The case of German engineers examining captured P-47 Thunderbolts stands as a stark and instructive example of the brutal realities of modern industrial warfare. Despite their sophisticated understanding and detailed knowledge, they faced insurmountable limitations imposed by their diminishing industrial resources. Their experience underscores a fundamental truth: technological mastery and tactical ingenuity can only extend a nation's reach so far if it lacks the capacity to produce and sustain the technology at scale. In the end, the industrial disparity between the Allies and Germany proved to be the decisive factor in the war's outcome, rendering even the most thorough technical insights insufficient to alter the inevitable. By the time of the Second World War, the nature of aerial combat had undergone a profound transformation. The advent of modern fighter aircraft was not solely about achieving maximum speed or maneuverability, but also about producing a machine that could endure the harsh realities of combat while delivering devastating firepower. Against this backdrop, the Republic P-47 Thunderbolt emerged as a remarkable symbol of American industrial prowess and military innovation. Its success was not necessarily due to being the absolute superior fighter in every conceivable aspect, but rather because it was a highly effective and robust machine produced in such enormous quantities that isolated instances of technical superiority became practically irrelevant on the grand strategic scale. During the war, American industry manufactured an astonishing total of over 70,000 fighter aircraft, a staggering number that dwarfed the capabilities of any other nation at the time. Among these, the P-47 Thunderbolt was produced in the tens of thousands, specifically 15,683 units. Alongside other legendary fighters such as the P-51 Mustang, of which 15,486 were built, the Lockheed P-38 Lightning, with a total of 10,037, the Grumman F-6F Hellcat, amounting to 13,738, and the Vought F-4U Corsair, with 12,571 aircraft to its name. This overwhelming industrial output was a testament not only to American technological capability but also to the vast manufacturing capacity that the United States possessed, capacity that the total German war effort, constrained by resource shortages and industrial limitations, simply could not match. Each fighter aircraft represented an immense investment of resources. Thousands of hours of highly skilled labor, tons of aluminum and steel, hundreds of precisely manufactured components, and the extensive capacity of American factories. Such scale of production meant that even if an individual aircraft possessed marginal technical advantages, its impact was greatly diminished by the sheer numbers of aircraft in operational use. The P-47 Thunderbolt, in particular, became a symbol of American industrial strength and resilience, striking fear into the hearts of German pilots who knew they faced a machine built for durability and firepower. German pilots, fighting against the Allies' overwhelming numbers, assigned the Thunderbolt a colloquial nickname, the Jug, a reference to its ungainly, heavy-set appearance. This moniker was a sign of both respect and recognition of its formidable presence. Additionally, some Luftwaffe pilots called it Indiana, inspired by the distinctive Thunderbird emblem painted on many of the aircraft's engine cowlings by various American squadrons. As the war progressed and losses mounted, and as the strategic situation for Germany worsened, some German pilots began to dismiss the P-47 simply as that 8-gun fighter. They learned through bitter experience to avoid engaging it at altitudes above 20,000 feet, where the turbo-supercharged engine granted the Thunderbolt a decisive advantage in performance, allowing it to hold tactical superiority. Throughout the conflict, the P-47 Thunderbolt demonstrated its resilience and versatility, with an estimated 3,752 enemy aircraft destroyed in aerial combat, an impressive tally, while approximately 3,499 Thunderbolts were lost to all causes, including operational accidents, mechanical failures, and ground attacks. At first glance, this near 1-to-1 ratio of losses to kills might seem modest. However, this statistic gains new significance when one considers that from mid-1944 onward, the Thunderbolt primarily operated in a ground attack role, facing intense anti-aircraft fire during low-altitude missions rather than engaging in dogfights. These missions involved attacking key ground targets and supply lines, often under heavy fire, which considerably increased the risk of loss. In the earlier stages of the war, during 1943 and early 1944, the P-47s served chiefly as high-altitude fighter escorts for bombers. In this role, where the aircraft's turbo-supercharger provided a significant advantage, the Thunderbolt achieved considerably better exchange rates, meaning it shot down more enemy aircraft than it lost. These high-altitude missions demonstrated the aircraft's formidable capabilities in aerial combat, reaffirming its reputation as a durable and effective fighting machine. Yet, it was in the ground attack role that the P-47 revealed another essential facet of American aircraft design philosophy: a profound emphasis on adaptability and toughness. When the P-51 Mustang, with its longer range and greater speed, began to take over bomber escort duties in 1944, many Thunderbolt groups were reassigned to tactical support roles. These missions involved providing close air support, attacking enemy fortifications, and disrupting troop movements at low altitudes, tasks that demanded exceptional durability and firepower. The rugged construction of the P-47, with its reliable air-cooled radial engine and heavy armor plating, proved particularly well suited for these arduous low-altitude operations. Its substantial size, weight, and armored protection made it less agile and more ponderous in a dogfight. But these features turned out to be advantageous when facing the dangers of attacking ground targets under heavy ante during the course of the conflict. The Allied forces documented staggering quantities of destroyed or damaged German military equipment, a testament to the intense aerial and ground assault campaigns. Official reports, corroborated by gun camera footage and after-action reviews, indicated that over 86,000 railway cars, an essential component of logistics and supply chains, were destroyed or rendered inoperable. Additionally, approximately 9,000 locomotives, vital for transporting troops and material across vast distances, suffered similar fates. The devastation extended further, with around 6,000 armored fighting vehicles, including tanks and self-propelled guns, being damaged or destroyed in targeted operations. The toll on trucks was equally significant, with an estimated 68,000 vehicles either destroyed or damaged, severely hampering German logistical capabilities. While such claims inevitably involved some degree of duplication or overestimation, the overall picture of destruction was undeniable, and the cumulative effect exerted measurable pressure on German military effectiveness. The relentless assaults by Allied aircraft, notably the P-47 Thunderbolt, played a crucial role in this relentless attrition. The P-47, armed with a combination of bombs, rockets, and its impressive array of 8 machine guns, had matured into a versatile, multi-role combat aircraft capable of engaging various targets with devastating efficiency. As the aircraft swooped low over enemy lines, German ground forces became increasingly adept at recognizing and fearing the distinctive sound produced by the Pratt & Whitney R2800 radial engines resonating through the air. The deep, rumbling roar served as a forewarning of impending attack, giving German troops little opportunity to prepare or evade. This auditory signature became a psychological weapon in its own right, instilling anxiety and fear among enemy soldiers who, for much of 1944 and 1945, faced a relentless barrage of air assaults. The sustained air campaign, coupled with substantial material losses, such as destroyed tanks, trucks, and logistical infrastructure, and the disruption of communication networks, gradually sapped the combat effectiveness of German ground forces. The cumulative impact of these factors cannot be overstated. It contributed significantly to the deterioration of German operational capabilities during the final years of the war. Turning to the fates of specific aircraft that were captured during this tumultuous period, a particular story emerges, one that provides an intriguing epilogue to the broader narrative of combat and destruction. Among these was William Roach's P-47D Thunderbolt, known as Beetle, bearing the serial number 42-22490 and designated T9+FK by the Germans. Remarkably, this aircraft survived the hostilities relatively intact and was recovered by American forces in May of 1945 at Göttingen, just as the conflict was drawing to a close in Europe. Following thorough examinations by American intelligence units tasked with analyzing German testing procedures, the aircraft was ultimately scrapped, its potential as a relic of wartime innovation thus lost. Similarly, Lloyd Hathcock's P-47D, numbered 42-75971 and also designated T9+LK, shared a comparable fate. Although recovered after the war, this aircraft was not preserved for historical purposes. Instead, it was dismantled or destroyed, erasing its physical presence from the collective memory of the conflict. The post-capture stories of these pilots diverged markedly different trajectories that reflect the varied experiences of those involved. William Roach, after his capture, spent the remainder of the war confined at Stalag Luft I, a prisoner of war camp located in Bath, Germany. His liberation came in May of 1945, when Soviet forces advanced into the area, freeing him and allowing him to return to the United States. Conversely, Lloyd Hathcock endured a grueling 11 months as a prisoner, mostly held at Stalag Luft 3, an infamous camp known for hosting the Great Escape, which had occurred just 3 months prior to his arrival. Notably, Hathcock was the sole African-American pilot among thousands of predominantly white prisoners detained there. When the Soviet forces moved westward in January of 1945, German authorities evacuated the camp under harsh winter conditions, forcing prisoners to endure a brutal march across the snow-covered landscape toward Stalag 7A and subsequently to Stalag 13D. Hathcock was liberated later, in April of 1945, by Allied forces. Upon returning home, Hathcock made significant contributions to the post-war integration of the United States Air Force, playing a pioneering role in efforts to desegregate the service. His career also included groundbreaking work in aerial reconnaissance photography at Wright-Patterson Air Force Base, where he advanced the technological and operational capabilities of aerial intelligence gathering. Meanwhile, Hans Vera Lear's wartime service was distinguished by his remarkable ability to operate an astonishing 125 different aircraft types throughout the conflict, including numerous captured Allied machines. His expertise as a test pilot, combined with an impeccable safety record, never experiencing a crash or serious damage, stands as a unique achievement in aviation history. After the war concluded, Lear provided extensive debriefings to Allied intelligence agencies concerning German aircraft development programs, offering valuable evaluation of captured aircraft, such as the P-47 Thunderbolt, played an integral role in shaping German understanding of Allied aviation technology during the war. The insights gained from examining these aircraft transcended mere technical curiosity. They revealed fundamental truths about the changing landscape of aerial combat and industrial rivalry. The detailed analyses carried out at facilities like the one in Vlan demonstrated that by the year of 1943, the decisive factor in determining the outcome of the air war over Europe was no longer solely the skill of the pilots, the ingenuity of tactics, or even the raw technical performance of individual aircraft models. Instead, it had become increasingly clear that the war's ultimate victor would be the nation capable of harnessing its industrial capacity to produce immense quantities of war material while effectively supporting its entire military apparatus. This realization underscored a harsh reality. The ability to manufacture adequate equipment at scale, combined with the capacity to sustain continuous supply chains and logistic networks, often proved more critical than possessing slightly superior aircraft or weaponry. Nations that could design efficient, reliable equipment and mass produce it in overwhelming volumes, enough to saturate the battlefield, posed a strategic advantage no amount of technical finesse could easily overcome. Conversely, countries with cutting-edge technology but limited industrial output found themselves at a grave disadvantage. By late 1943, Germany had become acutely aware that it was struggling to match the combined industrial might of its adversaries. The strategic position of Germany was increasingly precarious, facing formidable opponents whose industrial strength vastly exceeded its own, by factors of 5 or even more. When Britain refused to surrender after the fall of France, and when the Soviet Union managed to withstand the initial German onslaught and moved crucial industries beyond the reach of German forces, Germany's prospects for a quick victory diminished sharply. Additionally, the United States, with its vast, untapped industrial base, had entered the war, adding a new and formidable dimension to the conflict. The combined industrial capacity of the Allies made it clear that a military victory for Germany was no longer within reach. As the war progressed, The central question shifted from whether Germany could win to how long it could sustain its fight and what level of destruction would be inflicted before a final defeat was inevitable. The story of a German engineer known as Beetle, along with the collection of captured Thunderbolts at Rechlin, encapsulates this broader strategic struggle. These aircraft became a microcosm of Germany's dilemma. While German engineers could meticulously examine American aircraft, understand their capabilities, and assess the strength of Allied industrial efforts, such knowledge alone was insufficient to turn the tide of war. Gathering detailed intelligence, analyzing it meticulously, and documenting findings with precision were all vital steps. However, possessing comprehensive knowledge about American aircraft and industrial capacity could not compensate for the fundamental shortages of essential materials, aluminum, steel, rubber, fuel, as well as the lack of machine tools, skilled labor, undamaged factories, and reliable transportation infrastructure. The reality was stark. No amount of technical understanding could substitute for the sheer lack of resources needed to produce and sustain a war-winning arsenal on the scale required for modern, industrialized warfare. The German examination of the P-47 Thunderbolt at Rechlin served to reinforce this sobering truth about 20th-century warfare. The intensive study confirmed that material abundance, when coupled with expert engineering and effective tactical deployment, would ultimately prevail over raw technical brilliance constrained by resource scarcity. The most formidable aspect of the American arsenal was not any particular technological innovation alone, but rather the entire industrial system that could conceive, design, develop, test, produce, and support massive quantities of complex weapons systems simultaneously. This system was capable of maintaining high-quality standards, rapidly adapting designs based on battlefield feedback, and sustaining continuous production, an extraordinary feat of logistical coordination and industrial efficiency. The captured Thunderbolts vividly illustrated this lesson. German engineers measured, documented, and analyzed these aircraft with rigorous professionalism, providing detailed reports to their superiors. This knowledge was intended to inform strategic decisions and improve German aircraft development and tactics. Yet, by the time these insights reached the upper echelons of the German command, the war's outcome was already largely sealed. The lessons learned from the Thunderbolts arrived too late to alter the course of events significantly. As William Roach's aircraft, nicknamed Beetle, was undergoing meticulous examination, history was already moving toward its final act. The relentless march of the Allied industrial juggernaut had rendered the strategic battlefield a contest of resources and logistics rather than solely of technical prowess or tactical innovation. The story of the Thunderbolts and their detailed analysis encapsulates a pivotal understanding. In modern warfare, victory depends less on individual technological marvels and more on the comprehensive and efficient deployment of industrial capacity across every facet of the war effort. By the late months of 1943, when military analysts scrutinized the situation at Rechlin, it was clear that the trajectory of the war had already been shaped and sealed by the relentless power of industrial mathematics. This cutting-edge calculus of production, logistics, and resource allocation had reached a point where no display of German engineering ingenuity or the bravest pilot's daring could alter the inevitable outcome. It was as if the very fabric of victory had been woven through calculations and manufacturing prowess long before the final battles were fought. The sight of the Thunderbolt aircraft, parked on German airfields with hastily painted markings, overlaid with American stars that seemed to mock the original insignia, stood as a stark symbol of a future that had already materialized. This imagery reflected a profound reality. In modern warfare, the true battlefield had shifted from the skies or trenches to the factories and assembly lines. Here, Victory depended on the scale of industrial capacity, on the ability to produce vast quantities of aircraft, weapons, and supplies with unmatched efficiency. This era had dawned, where raw manufacturing power rivaled, if not surpassed, the skill of individual pilots or the sophistication of military technology, establishing itself as the ultimate determinant of war's outcome in the 20th century.